Well, I haven't done a video like this in a while. We're going to be programming another E2. This one is going to make ballistic range tables for us. And there's probably going to be some B-roll of like me inside the tank. But we're not going to be doing the sights. Okay, so rather than just go straight into the IDE, I decided it'd be kind of cool to put together a blueprint of what the chip should be doing. So at the very start of the chip, we're just gonna get some global stuff, things that'll always be the same. And then we're gonna start a timer. Now you might be wondering why the timer's so important. So to do ballistics, you actually need to run a lot of calculations. And we can use a while loop to do those calculations. The only problem is that there's so many that if you try to do them all at once, the chip will basically error out. You'll hit the tick quota. So 9 times out of 10, we're gonna start the timer. When I get down here, go to the while loop. So in the path like this, we're gonna do as many calculations as we can, and we're probably not gonna finish. So if we don't get to finish, what we basically do is just start another timer. And that is going to, it's basically gonna do a loop on itself. And if you're familiar with other programming languages, this kind of looks like a recursive function. It basically keeps running itself until it's done. So let's just say we do this about 4 times and the while loop is able to finish. So once again, we check if we've done everything we needed to do, and if we are done, we basically stop and don't start any more timers. Do you like what you see here? I know all this crap looks horrible. Let's start with this suspicious looking thing at the top here. So this is actually what ACF's code looks like. As far as doing shell flight, that is. I have my own version of that, so rather than trying to explain that, I'll try to explain my own scribble scratch instead. So ACF actually does calculations in 3 dimensions, because in Gary's mod you have X, Y, and Z. Everything's in 3-dimensional space. To build our range table, we only need to know how far the projectile goes and how much it drops. We're actually going to be using a vector 2 over here. Now, a vector 2 has an X and Y component. You might be familiar with this with the coordinate plane. This is how drag is computed. So, I have these 2 variables called old vel for old velocity and old position. And your drag depends on basically your current or old velocity in this case. So the drag is always in the opposite direction of your velocity. So I have the pseudocode here that's just old vel dot direction. So you might be somewhat familiar with drag. You have like this coefficient of drag here, and that's proportional to velocity squared. Now, ACF actually gives you a drag coefficient if you look on an ammo box or on an ACF gun, if it has a shell in it. Close. But there will always be a drag coefficient stored somewhere on the projectile, so that's nice. And you have this weird thing called the drag divisor. So another thing that the ACF code has is something called Excel. Basically, this thing right here. This is Yeah, you can even see it's gravity. And the gravity is the prop gravity. There is an expression 2 function that lets you get the prop gravity. Generally it's going to be negative 600, so I've just written it out as a vector 2, 0 on x, negative 600 on the y. Okay, so we got our drag, we got our gravity, and we have our old velocity. So we can use that to compute a new velocity. So you can see I have new velocity and new position. I'm not sure why I lost my colors, but yeah, new velocity, new position. So we start off with the new velocity. How do we do that? So we got our old velocity, and we're just going to add our forces because gravity and drag are forces. And we have to make sure the drag is being subtracted because right now it's positive. The drag variable we're storing it in. And we have this weird thing called a time step. So what makes projectile motion with drag so difficult is that you have this weird circular dependency where drag depends on your velocity, but your velocity also depends on drag. So I never took calculus. I did pre-calculus in high school, but apparently what you need to solve this is an integration method. And actually right here we have one. This is what an integration method can look like. This one is called Euler integration, and that's Euler with an EU. Basically all you do is you're basically stepping along with a really tiny time step, and in this case I know the time step is going to be roughly about 0.015 seconds, which I believe, so that's going to be like 15 milliseconds. This is about the tick rate of the typical Gary's Mod ACF or ACE server. So there are other integration methods. You might have, well, probably not actually. I'm not sure how common these things are, but ACF bulletometer, if you're familiar with that, or you ever come across that. That uses something called RK4. And actually there's an RK2 and an RK6, I want to say. Basically that stands for Runge-Kutta. I'm probably butchering that name. But the one we're going to be using is Euler's. They're all actually pretty simpler. I believe the Runge-Kutta ones are weighted averages. They're actually very interesting if you're curious about that. But if you wanted to use a different integration method, you would basically slap it in right here. Everything else will be the same drag calculation. This time step right here, this is the reason why we won't be able to finish in a single while loop. So the calculation for the new position, pretty simple. You just take the old position and you take the average of that old velocity and the new velocity. And because velocity is distance over time, if you multiply by time, you just have distance. So you just add your average velocity onto it, multiply by the time step once again. Okay, so I've drawn this graph here, and it's a little bit lopsided, not because of my drawing, it's also bad too, but on the x-axis we have a scale of hundreds of meters. On the y-axis we have a scale of tens of meters. Anyway, this is what you would expect, like, the path of a projectile to follow. So an interesting thing is we're going to be starting all of our projectiles off in a direction that is just positive on the x-axis, according to its muzzle velocity. And naturally it's just going to fall off and encounter drag and whatnot. You might think, the chip is gonna be able to make this like nice smooth curve. Actually, no, it's gonna be a bunch of tiny points, you know, stepping along. So it's gonna look something like this, and these are gonna be our little steps, these white dots. So the steps are basically a result of our calculation cycle here. And this is how we're going to be able to simulate the path of flight of the projectile. Something else that's not in my notes is, how do you determine when to stop the loop? So let's just say, okay, one good way to stop it is to say, I don't want to go past 700 meters. So you can say, okay, when the x-axis is past 700 meters, we're just gonna stop. So what if you have something else? So this is, let's just say, a really slow shell, and it's not able to go to 700 meters. What do you do then? Because then the chip will just run forever and never stop, right? So another thing you can do is you can look at the angle from the origin, right? So you can say, okay, whenever the angle to the last data point exceeds this, technically it's lower because these are like negative angles. What I mean is an angle kind of like this. You can check the angle, so whenever, so right here is where the cutoff will be in the case of this really slow projectile. You will start running your calculations and finish, and it looks like we'll finish at, I guess, 300, right? Because 300 just goes down here. Oh, 300 in a little bit, but it depends on your range table stepping. So we're basically gonna have two kill conditions, or stop conditions. One is like a max range, and the other is going to be a max angle. And basically both of these will make sure you get usable data without the chip hanging, which may or may not be a problem I had in a certain versions of my head chip. Anyway, that's enough theory crafting. Let's actually program the thing. I'm not sure how painful that was. We're just gonna go ahead and get started now. So let's open up an E2. Technically this isn't a brand new E2, I've given it a name, but this is what you'll see once you go on Reddit or something. Anyway, strict, don't need it. Trigger, none. And if you're wondering why I'm bothering with the trigger, it's because this will cause the chip to execute whenever an input changes. Versus inputs, outputs. Okay, we're good. Let's write an if statement. So this is what you might see in a lot of expression twos. If first or dupe finished or duped. I wrote this wrong. There needs to be parentheses to close the function. This basically makes sure the chip runs one time at the start. So what we're gonna do in here is make a timer. Let me just make sure I did this right. Yeah, okay. So the timer is a function, and this particular function, we go to the expression2 helper. This is really nice to use, by the way. So if we do timer, you can see it takes in a string and a number, sets a one-time timer with entered name and delay in milliseconds. So we're gonna do 15 milliseconds because that's about a tick, and we're gonna call it delay. How do we actually use this timer though? Well, so here's something interesting. So we're gonna start a timer, And the way we actually react to the timer is using this CLK, and it's got to have the same name as the timer. It is case sensitive as well, I think. But let's do something fun. Let's say about 1,000. So this is going to be 1 whole second, and then it'll print I to us. There we go. Very nice. Gonna put this back down to 15 milliseconds. So we kind of have our 2 parts already. We have the start block and the block where our while loop is gonna go. So this is what a while loop looks like. There are no conditions. So let's set something up that'll basically be our conditions. Okay, I don't want you to panic. So I have a number, which you could write a number at the end of it, but if you don't write anything at the end of a variable, it's just gonna assume it's a number. This number is something called data, which I've initialized to 1. If you do not initialize it, the compiler yells at you, like now. So just gonna initialize it so it's nice, green, and happy. Anyway, data. So we want to do some stuff. So while data is less than like a bunch of 9s, we want to run this while loop. Now this also might be something that looks really weird, but all this is doing is saying data equals data plus 1. So if data was just 1, you'd say 1 equals 1 plus 1, which seems mathematically incorrect, but because we're dealing with a variable, it's just gonna be 2, because 1 plus 1 equals 2. Okay. And this is a shorthand way of doing it. So let's run our while loop and see what happens. Yep. Hit quota. So remember what I said about the while loop. If you have a lot of things you're doing inside of it, it will hit quota your chip. So one thing we can do is there's this cool thing that you can use in while loops called perf. And it is also a function. So I believe we can do it like this. That finishes fast, I guess. So that basically stops the chip from hit quoting. So let's go ahead and print out whatever our data gets to. So as you can see, we're not done. It's not good. I kind of would like to be finished. So this is why the timer needs to come back. So here's the thing. We need to check if we're done or not. So you could probably write this all out by hand. However, I'm going to store this in another variable. Okay, so I'm in the middle of putting in something called run loop. It gets set to 1 initially, and there are no true and false statements in expression 2, even though you have if statements. But if you put 1 in an if statement, it's basically gonna act like a true. If you put 0 in an if statement, it's gonna act like a false. So this is basically saying while true, basically go ahead and increment your data, and after we increment, we're just gonna check, are we done, basically. So when we are done, we set this to false, which is 0 in this case. Now what we need to do is, this still isn't gonna help us because it's only gonna run once, as you can see. we're not hitting our 9999999. So all we need to do is just check if okay, so we have our first if and else stream. So if we complete the while loop and we still need to run, we'll just start that timer again. So you can see that whole circular thing that was in the blueprint, because this timer also has the same name as this timer, and this is where it's getting triggered. So we do a while loop, doesn't finish, just do it again. If this condition fails, the else condition will be triggered, and that'll basically just print out whatever our data is. Okay, so let's see what happens. There we go. So it takes a while, but it does get to 9999999. And that's the whole, first part and then while part done, which is nice. Another thing I want to say about perf is that you can put a number in here, 0 to 100, and if I put 25 in here, basically this controls just how much performance, I guess, a while loop is able to eat up. So if you give it more, it'll finish faster, but it'll eat up more performance. If you give it less, it'll take longer, but it won't eat up as much performance. Alrighty, we've graduated. This time we're actually going to be doing some ballistics. So let's go ahead and get started. So we don't need data anymore. We can go ahead and get rid of it. So let's figure out what we want to do, and I might set this to 50. So for sure we want a max range. This is going to be in meters, by the way. Let's do 4 kilometers. And yes, this hashtag is how you do a comment in expression 2. If you're used to other programming languages, it might look like a double slash, usually. I think Starfall even lets you do like 2 dashes. Whatever. We want this to be a persist. The reason we want it to be a persist is because we're going to use it in a whole lot of other places, and we want it to persist. So Gary's mod units are not in meters, they're in inches, so we need to pre-correct this. So I'll actually do it underneath here. This might look like black magic, but again, this is the short way of doing like something like this. So you do max range equals itself times 39.37. Yeah, but again, it's shorthand. So this will convert it from meters to inches. So we're gonna want an ammo crate. This is the first time I specified a type other than a number, by the way. It's gonna be an input. And sure, let's go ahead and add another persist line. Simple as. We'll make this on a vector 2. And this is gonna look rather strange. Gravity in Gary's mod. So if I do gravity. So if you ask for prop gravity, it's going to give you a vector. Now a vector is 3 components as opposed to a vector 2, which is 2 components. So we need to clean this up a bit. So again, on the x-axis we want 0. On the y-axis we're gonna get the prop gravity. So now we can't have a vector 3 in a vector 2, so we want the z component. This is how you get the z component. However, another way you can do it, and this will work with angles, vector 2s, vector 4s, whatever. We just want the third component, which is the Z. So there we go, we've cleaned it up, stuck it in a gravity vector 2. So there's something else interesting. I want something called a status. And the status is going to be a string. And what strings are is basically like text, basically. So let's go on our while loop, and we actually want to break it into two different components. Now, this may look really foreign and alien to you, but this is something called a switch case thing. I don't know. It's kind of like a super if statement. So basically it's going to compare whatever's in the switch to the case blocks. So I set status to initialize, and it's going to look at status, see what it is. If it's initialized, it's going to do everything in here. Anyway, we want to go ahead and get the muzzle velocity in the setup part. Another thing you might be looking at is this local tag. So you can think of all my other variables as global. Like you have status, you have run loop, you know, you have all this crap that I've yet to be using. This is only going to be able to be used basically in this case inside of this case. That's pretty funny. Anyway, so if I were to try to do something like this, undefined variable muzzle velocity, because this scope can't actually see muzzle velocity. Whereas if I moved it over here, we have no problem. Just a few compiler warnings. So we're actually going to want a few more vector 2s. If you want to specify multiple of a certain data type, you can put brackets around in the persist or output, input, whatever. So we're going to want the old pose. So let me actually take a look at my cheat sheet again, see what we need to do. Yeah. I'm gonna add another persist line just for organizational reasons. So yeah, drag coefficient we're gonna get off of the ammo crate. And we're just gonna initialize total time to be 0. So we want to go ahead and set up our old val. It's going to be equal to just a empty, well not empty, but a nameless vector. It doesn't matter. But what does matter is, remember, we want to start it off on the x-axis, so we have 1 in the x-axis, 0 on the y-axis. Positive x-axis, by the way. So we're going to do vec10 times muzzle velocity, and muzzle velocity is in meters per second. We want inches per second, so there we go, 39.37. And I believe we want to set old pose equals to a 0 vector, and then we can set our status to shell flight. Okay, so in shell flight, what we want to do is okay, we didn't want to do old, we wanted to do just the, and I'm not gonna call these new, I'm gonna call these shell pose. We actually wanted to set these because the olds just get set to whatever it was. It's fine, don't think about it too much. Oh no. Okay, so we're gonna do, we'll say old val equal to the shell val, and old pose equal to the shell pose. So this next part is going to be basically copy pasting ACF's code. So we figure out the drag first. Okay, I think I got it. So this is again local. This is going to change a lot, so there's no need storing it in a variable, process variable anyway. So what I'm going to do is get old val normalize. So this is kind of like getting the direction of a vector. Don't think about it too much. I'm gonna multiply that by our drag coefficient, which is gonna be multiplied by our velocity squared. And because this is a vector, we can use the length 2. This is basically the square length. So if I do length 2, there we go, gets the squared length of the vector, which is in this case the velocity vector squared. And we want to divide all that by the ACF drag divisor. Now we already have our gravity. It's a persist. We only need to get it one time. Okay, so now we can calculate the new velocity, which is shell val. So it's going to be equal to old val plus our forces. So gravity is already inherently negative, but drag is still positive, so we need to subtract it. And we need to multiply that by a variable we don't have called time step. What does that? Now, interesting thing about time step is ACF3's code, I should say, and AC's. This will work on AC as well, because all of the drag coefficients and divisors are stored places you can access them, but they will use the delta time, which will never go lower than the server tick rate. So let me see, tick interval, there we go. Now in my case the tick interval is going to be like 0.015. Again, it's the server tick rate. That's going to be in seconds, which is good. Okay. So to get the new velocity, we're just adding the forces multiplied by the time step to get the new position. Doing the old position plus the average velocity will work. I'm just gonna write it the way ACF writes it, which is like this. It's using this correction here. Again, you can just use the average velocity, but just to make sure everything is done the exact same way ACF does it, we will use this correction thing and just do that. It's basically accomplishing the same thing as taking the average velocity, multiplying it by the time step, and adding it to the old position to get the new position. Okay, so now we need our ending conditions. Let's see. Oh, we need to do this. So remember to, well, we're not using total time yet, but we'll just iterate on it. So again, we have this shorthand way of writing things. This is effectively just saying total time equals itself plus the time step. Don't think about it too hard. So yeah, ending conditions. What am I doing? So at our if statement, okay, I think that is everything. Now, one thing you can do is add some comments, so you know what does what. There we go. So I added some comments. So we have initialization, get some common stuff, so muzzle velocity, all that. Could be set some stuff too, because we want to reset the time step every time. And we can see, you know, we're doing our oiler integration, we're stepping along, and we have our termination conditions, which right now we only have one. So I should mention this. So we're only interested in the x coordinate of the shell position, and we're comparing that to the max range. And again, this stuff is also in inches. So whenever the shell position goes past the max range, we want to stop the loop. Okay, let's give this a shot. And spoiler alert, this thing will never end because the ammo isn't connected. So what we need to do is actually go ahead and wire the ammo up. But before we do that, I want to go ahead and fix this. So I'm not sure if you have the fix. You do have the fix. Here we go. So basically we will only ever kickstart the while loop if the ammo is valid. So now you can see we can update this chip. It does absolutely nothing. It doesn't hang or anything. But we can go ahead and check the ammo. And it's able to go and finish pretty quickly, actually. Yep. So we did it. It's done. Except we actually need to save the data, and it'd be nice to actually see what's going on. So we're gonna add some more things shortly. Well, this is a range table builder after all, so we'll need a table. Technically you can use an array, but we're gonna be using tables for a particular reason. This doesn't need brackets because there's only gonna be one table. And we will initialize it. So one thing I would like to be able to do is I'd like to be able to specify the range step. So in this case, there will be an entry every 100 meters out to 4 kilometers. And this also needs to be a persist. And we will need another variable. Entry range. Okay, let's see. So in our initialization, we want to initialize our entry range to be range step times 9.37. Okay, this seems fine. So back to this table. So you might be familiar with arrays. Basically, an array can hold a bunch of different numbers. So yeah, you can use an array to hold a bunch of different numbers, strings, vectors, whatever you want. In this case, it's just a bunch of numbers. You can mix and match things as well. One thing you cannot do in an array is hold other arrays. However, a table is kind of like an array. You are allowed to hold other tables in a table as well as arrays in a table. So yeah, table lets you do key value pair entries. So normally an array, this will be element 1, 2, 3, 4, and 5. However, a table lets you name things. Now you can do numbers in a table, so you can just do, I think you can do 1 equals. Yeah, but you can give things names. We're going to be using a table because eventually I want to be able to store multiple different ammo crates. The drop tables for multiple different ammo crates. However, we're going to start with 1. So we're going to make a new array in this table. So how does that look? Well, we'll say range table, and once again we can give this a name. So we'll say ammo-1. This is an array equals an array. So this is initializing it. So the table is going to be comprised of multiple ammo arrays. In this case, it's hard-coded to be ammo 1 because we only have the ability to wire up 1 ammo crate right now. Okay, well, let's see here. So remember, our position is going to be in inches, and we actually wanted to read out in meters. So what we'll end up doing is, instead of multiplying by 39.37, we'll just divide. So our data points are actually going to be vectors. Now they're not three-dimensional, it's just that I want 3 pieces of information saved, and a vector is quite convenient. So in the X position, or the first slot, is going to be the range, and the second slot is going to be the drop, and the third slot is going to be, oops, that should be total time. That's the time it takes for the projectile to do this range, basically. So how do we stuff the data into the table? Well, we do it like this. Actually, we're not stuffing it into the table, we're just stuffing it into an array that is already stuffed into the table. So we can use a function called push, and our data type is a vector. So we'll do push vector data. Let's just check and see if that is how we do everything. Yeah, and we want to make sure the entry range goes up. Okay, so let us actually, I don't think I ever need this else statement. So let's actually do something pretty fun. We'll print out what the Ballistics builder is doing. So to do that, we use print table because we're printing a table. Otherwise, it won't really work. And yep, there we go. So this is all in meters. We have 106 meters, about 1/10 of a meter drop, and it takes about a server tick to get there. Wow. Okay. I thought that was like, oh, never mind, that's 100 meters, so it's like several ticks to get there. Okay, that makes sense. And you can see we can go all the way down up till we get a little over 4 kilometers. Excellent. Now, it might be a moot point, but because of how I coded the while loop, it is possible that it skips over some data. Now, to be a bit extreme with this, if I were to have 1 meter range steps and have a 15 meter max range, so this thing is next to useless. You can see I only get 2 entries, even though it's the shell is able to do that. It should be able to fill up all the entries. One of the things we can do is we'll make a new variable called try step. And we will, an initialization of the, every new ammo type we'll do try step equals 1. Okay, what do we do here? So yeah, we just want to encapsulate all of this inside of its own if statement, so we'll only get more data if we're actually trying to step along. And we have never set try step to 0 yet, but we're going to set it to 1 again here. Reason being is because we're going to, anytime we need to make an entry, we're going to set it to 0. So it'll try to fill the entry before it tries to complete any new steps, basically. So we can just go to the very end and just set it to 0 whenever we're filling an entry. Alright, so let's see what that does. There we go. Oops. So we're able to get all of the entries off of the first data point. It needs to be cleaned up some. And we're able to get the first entry off of the second data point, however it terminates immediately. I need to do one more thing, and that is I need to say and the show pose one is greater than entry range. Is that it? No, it's something else. Alright, I gotta cheat. Okay, range, greater than max range. Okay. It's this. So our entry range is basically the range we're trying to make an entry for. So we need that to be greater than the max range, and then we can terminate. Let's try this. There we go, we're able to get all 15 entries. However, they need to be cleaned up. So let's clean them up. So right now all these entries are the same, which makes no sense whatsoever. Why we clean things up? Well, let's see here. So we're gonna want some space, so we're gonna need a thing called mix. I believe we use entry range. Yes, we do. So this might look really weird. So if you think about 0 to 10, if I asked you what number is halfway between 0 and 10, you would tell me 5. If I asked you what number was halfway between 2 and 4, you'd tell me 3. This mathematical equation is the same thing. The same sort of thing. So it's getting, instead of getting the number, it's getting the ratio though. So we want to make an entry for entry range, and that's going to be between old position and the shell position. And we want to get the ratio. Why do we need the ratio? Well, I'll show you. This is why we need some more space. Okay, so we're using our little mix decimal percentage number thingy, and we're using that in a function called lerp. It basically stands for linear interpolation. Now what this does is, again, if I were to ask you what number is halfway between 0 and 10, if you did lerp from 0 to 10 with 0.5, it would give you 5. So over here we're getting the basically decimal value, and over here we're using the decimal value to go between this number and this number. Might not making a whole lot of sense, but remember we have the distance, the horizontal distance, the drop, the vertical distance, and we have how much time is required to get to this distance. And we have total time, and we have the previous time, which is just going to be the total time minus time step. And we're just gonna stuff that inside of our array MO1. So let's see what this looks like. So immediately you'll see that our entries are cleaned up. So 1, 2, 3, 4, all the way to 15, right? And you can see we have much finer information now. So we're not just using the data points. We're actually using interpolated data points. So if I were to put this to something more sensible, like okay, range step of 200 out to 2 kilometers, Oh, that's the wrong button. Okay, so yeah, let's try this. There you go. So you can see, 200 meters, a drop of half a meter, and it takes about a quarter of a second, all the way out to 2 kilometers, drop of 50 meters, takes 2.5 seconds. Very nice. We've cleaned our data up. We're almost done. Just one more thing. So we have our range cut off. We need to add our angle cut off. And we need to go ahead and make this a persist variable. And the way we'll check this is this termination condition is getting very big, but we're just gonna add an or, that vertical line there. So we want shell pose, and there's a really neat function you can do, just to angle. And if you use this on the vector 2, it'll give you the angle of the vector 2. Now, because we're going down on the y-axis and positive on the x-axis, this angle is going to be negative, so we need to say if it's less than negative, angle cut off. And again, just to make sure we get all the data, just put this here, don't think about it too much. And try step, I think, right? I believe that's it for adding the angle cut off. You can see it doesn't really affect this data, but if I did something insane like 1 degree, there you go. Now, max range should be right at about 40 degrees. I don't say 45 because in the absence of drag it would be 45, but with drag it's closer to 40. So absolutely do not set this higher than like 45, and this should be able to weed out any projectiles that can't do your max range. But I'm gonna leave it to like 10. And we can set perf back up to 50. I don't want you printing to me, stop it. So we have a bunch of ammo crates, and I said I wanted to be able to do all these ammo crates, so let's go. We're actually going to use an entity marker which stores all of the ammo crates as entities inside of an array just called entities. So we need to make a few changes. So ammo is no longer an entity but an array. That means that ammo, we can't check if it's valid like an entity. We'll just check and see if it's linked to anything. So ammo count, we'll do that. So any reference to ammo isn't going to work. We'll just say local rate is going to equal to ammo. We need to get an index, so we'll need to use a variable called crate index, which will initialize to 1. So now that we know what index we want to work with, we can say crate index, and this is going to be an entity. So there we go. We can just use crate instead of ammo. Now when it comes to the name, so what do we do here? I guess we can do it here. Table name equals ammo dash and then crate index. So this will be like ammo 1 initially anyway, because crate index is initialize this one. And instead of using ammo 1 here, we can use table name. Table name. So our termination conditions are gonna have to be a little bit different, because when we're done with a particular ammo, we don't just stop the loop, we have to keep going. So we'll say So if there's more ammo crates to be done, we'll keep going. What we'll do is crate index. Hello, stop. We'll just plus. And that'll be fine. And if we are done, we'll actually go ahead and print the table out. Oh right, I need to set the status as well, so of course it's not gonna go to initialize if we don't set the status. So let's just go ahead and do that. There we go. This should work totally. Now of course I need to rewire the ammo. And let's see what happens. Boom. Now one annoying thing is this will print out of order for whatever reason. But we can see ammo 1. Now it's able to finish ammo 2. It's able to finish ammo 3. Able to finish 4. Able to finish. Now 5 is pretty low velocity. So it takes like 3 whole seconds to do 400 meters. Seems about right. And ammo 4 it takes like 6.5 seconds to get to 4 kilometers, which seems about right. And none of these exceed 10 degrees. However, if I wanted to do 5 degrees, clear this out. And see, ammo 4 starts to get cold a little bit, and ammo 1 can do all of 200 meters. So that's basically it. I'm gonna go ahead and add comments just so you don't get lost anywhere. I think I'm pretty happy with this right now though, so that's good. Go ahead and save that. So I've gone ahead and set up a few guns here. They all have differing muzzle velocities. Oh, there we go. So about 3, 4, 5, and 600. And I've set up a few targets along the flight path according to the range table. And if I just let these fire, they're able to hit the target. About, 48 inches across. I guess we can say margin of error, but the latter two seem to be a bit low. So that'll definitely ride. This is with AP. The other ammo types should work just fine because, again, the drag coefficient is stored on the ammo. Here's a case where it doesn't work, and I have no idea why. This is a machine gun. We're just gonna start firing it. So that block is positioned according to where the table... Wow, that's a bunch of crap. But according to where the table says the bullet should drop, and it's off. And I have 0.1 over here just to show you that this is where the 0 line would be. So I have no idea what's going on here. Assuming I'm just doing what ACF does, there might be something I'm missing, but I don't know what it is. So alright, well, that's it for this video. You should be able to use the range table to do some pretty cool stuff like make tank sights and actual range table sights. Looking at the record time, this one's long enough, so not gonna get around to that. Not today anyway. But anyway, if you had, well, I don't know, if you even bothered to follow along, if you got stuck somewhere, definitely let me know. I'm not sure if I should bother putting this trip up on GitHub somewhere. Maybe not. Maybe I will. Just make another slot for it. It'll be fine. Anyway, see you around.